All right, so in this video, we are going to dive a little bit deeper into what capacitance is and how it's calculated. So let's take ourselves back to our transmission line formulation. And we had equations up that simply told us what the capacitance is between two conductors for certain geometries that are common in transmission lines, like a parallel plate, a coaxial cable, a microstrip. In each of those transmission lines, there are two different conductors. And there's a direct coupling between the charge that appears between the two conductors, plus or minus, and the voltage difference or the potential difference between those two conductors. And that is connected through the capacitance. Now, in reality, the C that we put there was the capacitance per unit length. So any one of these transmission lines, as you make it longer or shorter, the actual capacitance of it is going to scale with the length. And so the true capacitance of the transmission line is going to be this value that we came up with times the length of the transmission line. And that should make sense. Let's think about this in the context of a coaxial cable. Right, so if I go back to Q equals CV, the most basic definition of what capacitance is, and I say there's a certain amount of charge here, there's positive charge on the outer conductor and negative charge on the inner conductor, I'm going to have to put a certain amount of voltage between these two conductors in order to build up that much charge. Now, if I make this transmission line suddenly longer by a factor of 2, but I put the same voltage across it, now I'm going to have double the amount of charge because I'm also filling up charge in the second segment. And so if the charge goes up, if Q goes up, but the voltage stays the same, that's equivalent to the capacitance going up. And so for that reason, you can see that as you scale the length of the transmission line, you're also scaling the capacitance because the same amount of voltage is going to give you more total charge stored along this transmission line. All right, but we saw these equations and we just sort of took them as descended from the heavens. And so now let's talk about how you might actually calculate this. Now that we understand that capacitance is really a consequence of electric fields in between the two conductors. So in principle, you can determine the capacitance for any situation that you think of, right? In this previous chart, these were just some examples, but you can make up any geometry where I have two objects and figure out what the capacitance is. And the process that we're going to go through, in principle, you have to integrate an equation. You have to integrate an electric field from one to the other. And in most real-life situations, we can't do that easily. If you open up a physics textbook or an engineering electromagnetics textbook, you'll find a small number of situations and you'll have the analytical solution. The most common one is a parallel plate waveguide that you may have seen solved before. But the number of examples you can actually figure out are pretty small. And you've either seen them all or I could just give you a few examples. So it's probably helpful to know that process, I guess, for conceptual purposes. But in real life, you can never really do this analytically. You have to do it numerically. So knowing how to do this numerically is much more important. Now, I will say that in the notes, I do have a specific analytical example of a parallel plate waveguide. So you can go through that. And the parallel plate waveguide is, I've got two plates right here. That was not good. Hold on. Got two plates right here. They are separated by a distance of d. And there is a charge positive Q on one and negative Q on the other. By definition, as you calculate this, the two conductors always have positive and negative of the same charge. There's a distance d between them. You can define a coordinate system here. This is y. This is x, and this is z. And our question is, if I put this charge, positive Q on one plate and negative Q on the other, what is the voltage change between them? And the way you'd go about this is, first, you'd figure out what the electric field is everywhere. And that's relatively straightforward because we know what the electric field is from a sheet charge, right? The electric field from a sheet charge is rho s over 2 epsilon, and it's going to be plus or minus that in the z direction from each of these charges. And so the contribution of both charges is going to end up being right? This is from one sheet. From both sheets, it's going to end up being rho s over epsilon, the charge density. And remember that rho s can simply be the total charge Q divided by the area of the plate. Right? And so you put all this together, and this ends up pointing actually in the negative z direction. And so once you know the electric field, you could then integrate the electric field from the top plate to the bottom plate, from the positively charged plate to the negatively charged plate. And when you do that, you'll be calculating the voltage difference, because we've got the line integral from point A to point B of E dotted with dl is going to be equal to VA minus VB, the potential at point A minus the potential at point B. And so with this, you can figure out that for a parallel plate waveguide, you've got that the capacitance per unit length equals epsilon times the area divided by D. And that exactly matches what we have in our notes from the transmission lines, right? So this is a simple example. In reality, though, this is not going to be solved analytically. What you have to do is you'd have to set this up numerically. So once you set up these charges, you'd use some method to sort of determine what is the electric field everywhere. Right? Maybe you could sum up Coulomb's law, or use some technique to figure out the electric field, and then you divide up the space in between the two plates into small little segments, and you can take the integral of the electric field along this path between the two plates. What makes this a little bit easier, you can choose any path you want. You can take the line integral from the edge of the top plate, loop around, and come to the bottom. You can go straight from the top to the bottom. You can go off to, all the way out, loop around, meander like crazy, then come down to the bottom. No matter what path you take from the top to the bottom, you're going to arrive at the same answer. So you can select whatever path integral you want in order to calculate it. All right. Now, the last thing we're going to cover in video number 3 is we're going to cover the fact that this capacitor right here has to store electrostatic energy. Every time we pull two charges apart, we are adding energy to the system, because I could release that charge and it's going to want to come back together. And that potential energy is something we can quantify. And that's going to give us some insight into the nature of electric fields. And we'll cover that in the next video.